In this example, we have a train that leaves a station starting from rest. In the first 20 seconds, it speeds up to 10 feet per second, and then it holds that speed for 60 seconds. Then it slows down to a stop over a period of another 20 seconds. We need to draw the AT, VT, and ST graphs and find out how far did the train travel. Well, let's start by drawing our VT graph. I'm going to leave a little bit of space up here at the top so that we have room for our AT graph. And we'll put the AT on the top, the VT in the middle, and the ST at the bottom. So this is my velocity and my time. So for the first 20 seconds, it starts at rest and speeds up until we get to a speed of feet per second. Then we hold that speed for 60 seconds, and then it slows back down until it comes to rest. So this point would be 20 seconds. This point is 60 seconds later, so this is at 80 seconds. And then this point is at the end, which is another 20 seconds later, so we're at 100 seconds. Because he holds the speed at 10 feet per second, we have 10 feet per second here as well. Now, let's look at the acceleration time graph. Because our velocity here is increasing from 0 to 10 feet per second at a constant slope, that means that we have a constant acceleration. And the slope of this line would equal what our acceleration is. Our rise is 10 feet per second, and our run is 20 seconds. So we've got 10 over 20, which is 1/2, or 0.5. So our acceleration, extend this dotted line up here and this dotted line up so that I can see the transition points on both graphs. So I accelerate at 0.5 feet per second squared for the first portion of this problem. Then I go at a constant velocity. If I'm going at a constant velocity, my slope of this line is 0, so my acceleration is also 0. And I can connect those like this. Then in the final part, I've got another 10 feet per second rise and a 20-second run, but this time my slope is negative, so my acceleration is negative 0.5 feet per second squared. So that would complete my acceleration time graph. Next, let's move down and draw a position time graph. So this would be position, this will be time. Again, I'm going to extend my dotted lines down through. Alright, so we know that the velocity represents the slope of the position graph. So if my velocity at the beginning here is 0, then my slope has to be 0. And if my velocity on my VT graph is 10 feet per second, then that slope on the position graph has to be at 10 feet per second. And we'll just draw that in there representatively. To find my position, the position is the area under the velocity graph, because we know that velocity is equal to ds dt, or the integral of the velocity with respect to time is equal to position, which means that position is the area under the curve. So if I look at this area, I've got a base of 20 times a height of 10, which is 200, but because it's a triangle, we divide it in half. So my position after 20 seconds would be 100 feet. Now, because this is a constant slope, that means it's a first order equation, which means that we'd have a second order equation here. So we would have a curve that would come up until we hit the slope that we defined at this point. Next, the slope of the position graph represents what the velocity will be, and we have a constant velocity, so we'll have a constant slope. But we need to find what the position is at the end of that portion of the velocity time graph. If I look at the area under this curve, from 20 to 80 seconds, that's a 60-second period at 10 feet per second, which gives me 600 feet. But we've already gone 100 feet, so we need to add that 100 to it, or we add this area. So we add 100 to our 600, which will give me 700. And we know that the slope is continuous, so it's a straight line in that portion. Then finally, we start slowing down. So we go from 10 feet per second to 0, and the slope is the area under this curve would give me what my final position is. We start at a slope of 10, we end at a slope of 0, and this area is 10 feet per second times 20 seconds divided by 2, which would be 100, which means that we're going to stop here at 800 feet. And because this is a first order line, this has to be a second order polynomial curve, so it's a curve that's concave downward. And that gives me my position time graph with all of the representative times. And we know that our final position now is equal to 800 feet. And that's the end of the problem.